So I'm sorry I forgot to hit record here. If you're watching this for the first time because you weren't here in class today, we are on page 38 of your unit handout. When you look at the first field that I've given you, it's a heat field of a specific source, the fire in the middle of the classroom. The light field is of a specific source, a particular light bulb. The sound field is from a particular source. This field that I'm talking about here is a field that's gravitational, and it is the specific gravitational field having as a source the mass of the Earth. I don't want you to think that all gravitational fields are the gravitational field of the Earth. If I wanted to talk about the gravitational field of Jupiter, then I would use the mass of Jupiter as the source. The test object is anything, this is crucial now, this becomes very specific and not flippant like the other ones. The source here must be something with mass. Sorry, the test object must be something with mass. So we have the source of the Earth's gravitational field is the mass of the Earth, and if we want to know what the influence is experienced by looking at a test object in the field. Now, I know that your chart is filled out for you, but if I were to ask students what is the influence on an object put in the Earth's gravitational field, most people will say that when I put an object in the Earth's gravitational field, it will accelerate at 9.8 meters per second squared. And I will say, no, you're wrong. That is not the influence. Are you right now in the Earth's gravitational field? Definitely, you all are. I'm assuming that nobody's taken a journey in the last 24 hours and you're still on Earth. Are you experiencing something because of the Earth's gravitational field? Yes, you're experiencing a gravitational force down. The only way your influence would be an acceleration of 9.81 meters per second squared is if you were in free fall. So yes, if you were to climb up on a chair and jump off of the chair while you are in free fall, that's your acceleration. But the fact of the matter is, the influence of the Earth's gravitational field is a gravitational force. That's what the influence is. So the influence is a gravitational force on the test mass near the Earth. And now we're going to answer a few questions about fields in general. So first of all, in any field, it's the amount of the influence that kind of tells you the size or the strength or the magnitude of the field. So the higher the temperature, the stronger the heat field. The more squinting that happens, the stronger the light field. The more intense the headache, the stronger the sound field. And of course, in a gravitational field, the greater the gravitational force on the test mass placed in the field, the stronger the gravitational field. I want to be very clear about something here. Force and field are different things, though. This is really, really subtle. It's like weight and mass. You know, people interchange the concept of weight and mass all the time, but in a physics field, I shouldn't use the word field, in an area of physics where we study physics and science, weight and mass are different. Well, the same thing with force and field. They are not the same. This is really, really crucial. You're going to confuse them. You're going to be doing calculations later in this course and later in Physics 30 where you'll say, I'm getting the wrong number. And I'll say, well, because you're finding the force and it doesn't want the force, it wants the field. I think a very important way to look at what a field is that a field is something in physics that we use to explain the production of a force. So why do electric forces on charged objects exist? Well, because there's electric fields surrounding those objects. Why is it that, I mean, as kids, we've all played with magnets, right? Take some fridge magnets and you play with them, and you put them one way and they push away. You put them another way and they repel, or you put them the other way and they attract. I mean, you might have even been playing with some of these magnets this weekend. It doesn't have to be when you're a kid, right? Magnets are interesting. The reason why magnetic forces exist is because magnetic fields produce the forces. And by the way, a force may result in an acceleration if there's a net force. So this little visual here, I think, is kind of important. A field, a force, and acceleration are all connected, but they are different from each other. A field is the cause of producing a force, and a force is the cause that may produce an acceleration. So now, back to the idea of fields. There's two types of fields. There's a scalar field and a vector field. The meanings behind scalar and vector here have not changed. If I were to go back and look at this chart, and you look at the influence, does temperature have a direction? Do I say to you that this morning it's 8 degrees below zero east? No. People would start to look at you funny if you said stuff like that. When you talk about the amount of squinting, would you say it's fairly intense squinting south? That doesn't make sense. Your headache has no direction. But the gravitational force on a mass in the Earth's gravitational field does have a direction. And that means that gravitational fields, of all four fields I've shown you today, gravitational fields are vector fields and the other are scalars. Now I have a question for you. It's going to require some thought. In general, what two things determine the strength or the size of the influence on a test object placed in a field? But here I want in general. I don't want specifics. Some of you might say, well, I can get a greater influence if I put more fuel on the fire. Well, that's true. But you're not going to change the Earth's gravitational field by lighting it on fire. So what I'm interested in is two different things that determine the influence of any field. And these are going to be true whether it's electric, gravitational, magnetic, nuclear, electropotential fields, all kinds of fields. So I just want to give you a minute here to write down. You might want to use a pencil, or maybe don't write them down, but just have them in your head. And then in a second, I'm going to ask for some ideas. So who can come up with one general thing that determines the size or the strength of the influence? Okay, so Andrea says mass. I'll get back to Evans in a second. Andrea says mass, and although, Andrea, that is true for the gravitational field of the Earth, if we had a greater mass, and by the way, well, I better ask, Andrea, mass of what? In our specific example, okay, so everybody just slow down for a second here, because I want to talk about Andrea's answer, and I'm only seeing the chat line at a time, so when you start typing stuff, it goes off the screen. You're right, Andrea, it would not really work for the other ones. And by the way, so it's not general enough. And by the way, I hope that by mass you meant in our example the mass of the Earth. That would change the gravitational field. Okay, so I didn't. I just wanted to make sure you didn't mean the mass of the object you put in the field, because the Earth's gravitational field should be the same whether I talk about, myself being influenced or a vehicle being influenced. So I want to just give me a second here. I got to scroll up in the chat because I got a few messages that went off my view. So I want to talk about Evan's answer, which is intensity. And this always happens whenever I ask this question. Intensity is not a good enough answer because intensity is basically the word we're going to be using for strength of the field. In other words, if you just say the intensity, I'm assuming you're saying the intensity of the influence, but the strength of the influence is the intensity of the influence. So you would be answering the question by just using a different word to mean the same thing as what's in the question. We want to drill down. I know what you mean by intensity here, Evan, and it's a very hard word. The word that you're searching for is very hard to come up with. Liam said field density, and it turns out that the phrase field density is actually what we're after here. So to Liam, what I would say is, what two general things determine the field density? So, and I don't want you to type an answer just yet, it's just for you to think about. So what Evan and Liam both did was they answered the question very correctly, but they ended up just using words that meant the same thing as what we're asked to describe. JV said distance from the source, and that's the first very general statement that is correct for all of these fields. The distance from the source. If we take a look at all of these, and you imagine there's a certain temperature on the thermometer, will that temperature, which is the influence, be different if I move closer or further from the fire? Of course it will be different. If I'm standing 50 feet away from a lamp, I don't know why I'm doing this, and I'm looking right at the light bulb, there might be a level of squinting, but as I get closer and closer and closer and closer to the lamp, the amount of squinting goes up. And by the way, as you get closer to the fire, the amount of temperature goes up. If I decided, because I've just had enough, I'm going to walk across the street and tell those people that, please, could you do me a favor? I'm an old guy, I'm already deaf in one ear. Can you turn the music down? Great song, I like it, but I just want you to turn it down. As I get closer and closer to the vehicle, my headache, I'm being facetious here, but my headache will increase, right? The intensity gets greater. And we have already learned, this is why I wanted to talk about this earlier, we have already talked about the fact that when you get closer to the Earth, which I am in central Alberta, the gravitational force, my weight, will be greater. My weight depends on the location. And in all of these cases, if I get closer to the source, the field strength increases. So let's write that down. So in general, one of the things that determines the strength of the field is the distance to the source. And I can summarize that by just saying the location. If a field is this three-dimensional region of space that influences objects, then if you're in a different location, you might get a different influence because you're closer to the source or further from the source. There's one other thing, and this is the thing that Liam and Evan both, I think, have in their minds, but it's a very hard thing to come up with a word for. Now, Mackenzie said, would it have to do with the distance an object is away from a field? No, that doesn't make sense, but if you change, Mackenzie, that word field to source, that's exactly what we've been talking about. It has to do with the distance that your test object is away from the source of the field. Good. So there's one other thing, and again, I think when Evan said, I think, I'm going to scroll back up. When Evan said intensity, and I think Liam probably said, did you say line density? Field density. When Evan said intensity and Liam said field density, they both kind of mean the same thing. They're searching, I believe, for a word which describes the idea they have in their heads. And I'm not a mind reader, but I've taught this enough to know. Can somebody come up with a word? There's one other thing here. Can you come up with a word or a description for what the other thing is? I mean, I could just give it to you, but I think thinking is an important part of learning. I really believe that. Okay, would it be safe to say that in the case of the heat field, the other thing other than how close you are to the fire would be how big the fire is? That would change the field. And would it be safe to say in the case of the light field that, imagine the lamp is on a dimmer switch and I can increase the voltage to the lamp, that not only does it change depending on how close I am to the lamp, but it changes depending on how bright the lamp actually is. And, you know, the people sitting in the car listening to the song can increase the volume. So if I'm standing a certain distance looking at that and getting annoyed, there's a certain intensity, and when they increase the volume because they see they're annoying me, they increase the volume, the intensity gets even bigger. I don't have a dial on the Earth, but I could go from the Earth to a planet with more mass. Charge, it turns out, Mackenzie, is not the word to kind of summarize all of those things, because charge is actually the name we give to the source of an electric field, just like mass is the name of the thing we give to the source of a gravitational field. So I will let you guys off the hook. The word that after close to 25 years of teaching, a student came up with a couple of years ago, which summarizes it perfectly, is the following. The awesomeness of the source, the greatness of the source. Some people in the past have said the size of the source. I may have spelt awesomeness wrong. Some people have said, well, it's the size of the source. And then I would respond saying, is a larger light bulb necessarily brighter? And the answer is no. Is a larger fire necessarily hotter? And I would say no. And the reason why a larger fire is not necessarily hotter in terms of temperature is if you've ever welded, you have a very small fire. No, not even welded. Soldered. If you've ever had a soldering torch and you're soldering something, you have a very tiny fire, but it is very, very hot. So what we're talking about here is the greatness of the source. Yeah, and Mackenzie, charge was just another thing that was too specific. But the charge of the source is the thing that determines the strength of the field for an electric field, as well as the distance to the source. The mass of the source is the thing that determines the strength of the gravitational field, as well as the distance to it. Second question here, does a field still exist if there's no test object within the field that can be influenced? This is kind of like the old, if a tree falls in the forest, does it make a sound if there's nobody there to hear it? And the science answer to that question is yes, there's a sound, because sound is a movement of air that we will talk about in the next unit. And the bottom line is the field still exists whether we put an object in the field or not. You know, the field itself is the region of space that would influence something if you put it in the field. So a really kind of frightening thing to think about, but imagine if all of a sudden the only thing in the universe was the Earth. there were no masses we could put in the Earth's gravitational field. Would the Earth still have a gravitational field? Yes, because it would still have an area of influence that would influence a mass put in there. So now we're going to talk specifically about gravitational fields. So a gravitational field, and there's the symbol for it, is an area of influence, apparently this is on the next page, is an area of influence surrounding a source mass. The gravitational field of the Earth is the area of gravitational influence surrounding the mass of the Earth. In this case, the mass of the Earth is what we call the source of the Earth's gravitational field. And any object that you put in the field is influenced by a gravitational force. And the object that you put in the field is called the test mass. So it's really important you understand the difference between a source mass, which is the thing that creates the field, and a test mass, which is something you just put in to see what happens. Now, gravitational fields are vector fields. They have to have a direction and a strength. So this phrase here, intensity or strength, this is why I think it was Evan who said intensity of the source. We don't want to use that word. The intensity of a field, gravitational field, or the strength of the field means the magnitude. So all vectors have magnitude and direction. Okay, a gravitational field has a magnitude and a direction, but we call the magnitude intensity. Obviously, the direction of the gravitational field surrounding a source mass is going to be towards that source mass. It will be the direction of the influence on any test mass within the field. And what I'm showing you now here is a way to visualize the Earth's gravitational field pictorially. Now, this is just a flat representation. In reality, if you took a little sponge model of the Earth and you put pins in it everywhere, not just in a circle that I'm showing, but pins entering from the front and entering from the back, that would be a three-dimensional representation. I have a feeling I've got something more here. I do. So this is the gravitational field diagram for the Earth's gravitational field. I would like you to notice that the direction of the field is indicated by the arrows. And the strength of the field, the magnitude of the field, is indicated by something which Liam said earlier. Liam used the words field density. And density means how close things are together. So the population density of the Philippines is about 50 times as dense, I believe, as the population density of Canada. It's a very, very tiny country with a lot of people. So people are closer together in general. Canada is very spread out. So what we say here is the strength of the field is indicated by the line density. This is the phrase we're going to be adopting. And just in general, I hope you can see that the lines at this location in space that I've marked in yellow are closer together than the lines are at the bluish-green location in space, which means that the field intensity or the line density is greater at the yellow point, so the gravitational field at the yellow point has a smaller magnitude than the gravitation, has a larger magnitude, my eraser not working, has a larger magnitude than the gravitational field strength at the green one. The closer you are to the source, the greater the strength of the field. It appears as though in physics and the universe, that's true for any field. We have never discovered a field that if you get closer to the source, the field gets smaller. All right. So now, how can we describe the field, the gravitational field of a planet mathematically, which is more useful? Second way to describe it is to define it mathematically, and here is the definition. This is a definition. Gravitational field strength is defined as the ratio of the gravitational force on a test mass to the mass. For example, the strength of the Earth's gravitational field in central Alberta is 9.81 newtons per kilogram. Not meters per second squared, newtons per kilogram. It's a ratio of force to mass. That ratio that you're looking at, which I'm just going to write and talk briefly about, means it's a ratio of 9.81 newtons to every 1 kilogram of mass. This is a test mass placed in the field. If I put 1 kilogram of test mass in the Earth's gravitational field in central Alberta, the influence will be 9.81 newtons. If I were to put 2 kilograms of mass, then it would be 19.62 newtons. And if you take your calculator and divide 19.62 by 2, you get 9.81 newtons per kilogram. And I guess what I'm telling you right now is we can write 9.81 newtons per kilogram or 9.81 meters per second squared, and those units are equivalent. I do not want to spend time today explaining why they are the same sets of units, but they are. Okay? Which is why, I better say this now. From now on, everybody, when we find the weight of an object using force of gravity equals mg, and let's say the mass of the object is 3 kilograms, I will no longer be writing 9.81 meters per second squared. Because this 3 kilogram watermelon that's sitting on my kitchen counter is not accelerating, but it is in a gravitational field. And you can see what happens here. It's very nice. The kilograms cancel and you're left with newtons. So we're basically using this formula right here, which I've left the vectors out of it because the directions are pretty obvious. They're towards the center of the Earth. The mass here is the mass on an object put in the field. It's the test mass. Now, I want to point something out to you. This is tough for me and for you, for me to explain. The two things you said determine the gravitational field would be the mass of the source of the field and the distance away from the source. But if you look at this formula I've highlighted, the distance away from the source is not there, and the mass of the source is not there as well. So we're going to be working in a few minutes on developing a better formula, one that we could use the mass and the distance to calculate the field. But let's talk about this formula a little bit. What I've got here is just a little thought experiment. We've got the Earth. This little alien comes down and lands on Earth. His or her galactic leader has tasked this thing with determining the gravitational field strength of the Earth so they know what kind of armor to have when they invade Earth. This guy's name is Marvin. Actually, that's his name, but I don't know how to pronounce it, so his name is Marvin. And Marvin has taken high school physics on his or her planet. So they know to calculate gravitational field strength, you use gravitational force on a test mass over a mass. Marvin has come prepared for all of his scientific experiments, so he has in his spaceship a series of test masses, and he also has a spring scale which he can hang the test masses from to determine the gravitational influence. So what does Marvin do? He puts a 500-gram mass on the spring scale, and he reads the spring scale very accurately. It's a magical spring scale that's perfect. There's no error in the measurements. And he gets 4.9 newtons. So do me a favor, please, people, and take your calculator and take 4.9 newtons divided by 0.5 kilograms. He discovers for his first data point that the gravitational field strength on the surface of the Earth is 9.8 newtons per kilogram. This is okay, but I've learned in science that I should take multiple data points, so he puts a kilogram on there. He measures the force using the spring scale, and then if he divides them, I hope you don't need a calculator to divide 9.8 by 1, you get 9.8 newtons per kilogram. If he puts 1.5 kilograms on there, in fact, you should be able to figure out what he reads. See if you can figure out what he should read based on the previous data. And you might need a calculator to do this. Yeah, 14.7, because 14.7 is the number that you divide 1.5 by to get 9.8. All of these numbers in the third column are the force he measures divided by the mass. If you were to put a 2 kilogram mass, it turns out he would measure 19.6. And on it goes. Whoops. So this is just something that you can look at to visualize what we're talking about here in terms of gravitational field strength. This is the definition of gravitational field strength. It's where we get the weight formula from. So I don't know if you remember, but if you were to go back and watch the video for the lesson on weight, or go back and look at our notes, we defined weight and we came up with that formula in a really, really bizarre way. But the formula for weight is m times g. Okay, so now we want to do something else. The above definition is okay, but I don't know if this is obvious or not. I'll just throw it out here and hopefully it sticks. If you knew the mass of Mars, and you knew the radius of Mars, then you should be able to find the gravitational field strength on Mars. Because you have said, and I've told you you're right, the only thing the gravitational field strength depends on, in fact, the only thing that any field depends on, is the size of the source, which would be the mass of Mars here, and how close you are from the source, which would be the radius of Mars. Notice that I'm using capital M for the mass of the source here. So let's take a look at this warm-up question number 3 now. We've got the Earth, which has a mass, capital M, and that's the source. We've got a satellite in orbit that has a mass, and that's the test mass. And there is a gravitational force on the satellite. So the first question is, write an expression for the gravitational field at the place where the satellite is. Well, we know this. Gravitational field equals the gravitational force on the test mass over the mass. That's it. That's all we're asked to do here. So if you knew this force and you knew this mass, you would divide them just like Marvin the Martian did in his experiment. Okay, second question. Use Newton's universal law of gravitation to come up with a different way to calculate the gravitational field strength. So here we go. This is how we calculate the gravitational force between the mass of the satellite and the mass of the Earth. I've replaced M1 and M2 here, everybody, with mass of the test object, which in this case is a satellite, and mass of the source, which in this case is the Earth. But what we're doing, we could do for any planet and any test object. I'm going to divide both sides by the mass of the test object. And I get the gravitational force over the test mass is equal to capital G times the mass of the source over r squared. Okay. So what? Well, this is pretty cool, you guys, because the definition of gravitational field is this. That's the definition of gravitational field. But it's equal to gm over r squared, where m is the source. And what that means is that the gravitational field strength can also be found by using this formula. I would like everybody to do me a favor. I would like you to grab your calculator and calculate gm over r squared using the mass of Earth and the radius of Earth. Take 6.67 times 10 to the negative 11, multiply by the mass of the Earth, which is 5.97 times 10 to the 24, and divide by the radius of the Earth squared. I'll make sure I've entered it correctly. 6.67 times 10 to the negative 11 is capital G. The mass of the source of the Earth's gravitational field is the mass of the Earth. And the distance from the center of the source when you're on the surface is that number. We have to square it. 9.81. This is why the Earth's gravitational field strength on the surface is 9.81. Before I forget, remember yesterday, I think it was questions 7 and 8 from the previous day's assignment, we were off by a Newton or two from the answer? It occurred to me, as I'm waiting for in my doctor's office yesterday, it occurred to me the reason why. There was a time on the formula sheet where the mass of the Earth was 5.98 times 10 to the 24. And it changed to 5.97. And the physics data sheets that they use in Alberta are updated regularly, so more accurate determinations of the mass of the Earth put it now at 5.97. So I think if you do the calculations with 5.98, you get those answers. Those questions I had typed up and made when we were using the old formula sheets. Okay, so let's take a look now at the summary here. The summary is that you have two formulas for gravitational field strength now. If you know the test mass and you know the amount of influence on it, then you can do what Marvin the Martian did to determine the gravitational field strength of the planet. If you know the mass of the planet and the location that you are at, wait a minute, field strength is determined by two things. Mass of the gravitational source and distance from it. That's now in the formula. So now we only have one example. On your formula sheet, this is what we are dealing with. We have Newton's universal law of gravitation. This is used to find a force. However, if you want to find a field, you use this. A very common mistake when finding a field is to end up using the yellow formula by mistake. That's a force. All right, I want to take a pause here. I know it's a long lesson, it is. We've been at it for about an hour here, hour and a half rather. No, an hour. But too fast, too slow, just right. Please and thank you. Okay. Thank you. And I don't know if I said, but we're only doing one lesson today. We only have one example here. It's got numerous calculations here. But we're going to be using for question 1A the formula that we have just learned. And, oh, by the way, I can't tell you the reasoning why this formula has an absolute value sign around G and this one doesn't. In my mind, having them both with absolute values is kind of the way to go. So I very rarely use vectors here. I just know that gravitational field direction is towards the center of the planet. So we're going to use this formula, G equals Gm over r squared. If you take a look at the formula again, you'll notice that it just has m, right? It doesn't have m of the source. And down here, it doesn't have m of the test object. Both of these formulas that I've highlighted in blue-ish green simply have m. But you need to know that in the first formula, the m is the source, and in the second, it's a test object. So what are we going to get? We're going to get the mass of the planet times g. G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. I would like you to put the units in this time. Multiplied by the mass of the planet, 4.55 times 10 to the 25 kilograms. Divided by the distance, which is the radius of the planet. In this context, 2.5 times 10 to the 6 meters, quantity squared. So we're going to calculate the local value on this planet of the gravitational field strength. Just double check. And again, when I double check, I think you should get in the habit of double checking too. There's a lot of numbers that we're throwing into the calculator here. I have G, I have the mass of the planet, and I have the radius squared. I'll just make sure I copied them from the question correctly. I think we're okay. So what I get is, do you get that? That doesn't seem right to me. Is that what you get? Okay. Oh, maybe I did that intentionally. So we get 486 newtons per kilogram. Now, just a second here. G on Earth is approximately, those two wavy lines are like an equal sign, but it's not exactly equal. I will use this number a lot. G on Earth is about 10. It's 9.81, right? That's pretty close to 10. How many times larger is the gravitational field on this planet than on Earth? Is it twice as large? Is it 5 times as large? Well, with the number 10, it's easy to see that this is about 48.6 times the gravitational field on Earth. What does this mean? Think about you walking up a flight of stairs. Or better yet, think of you doing a chin-up. there's a certain force that you have to apply to pull yourself up. The force that you would have to apply to pull yourself up or to walk around on this planet would be almost 50 times the normal force on Earth. So it would be like, if you were to try to walk around on this planet, having a backpack on your back with 48 of you in that backpack. You know, if you were to carry somebody piggyback on your back, that would be what it would be like to walk around where G is twice as great. If G is 5 times as great, you've got 5 people you're carrying around. If G is 50 times as great, you're carrying 50 people around. In other words, you wouldn't be able to move on this planet. You would just be a broken rubble of biology laying on the surface of the planet. So now, what are 2 different interpretations? One of them is 486 newtons per kilogram, and one is 486 meters per second squared. Those are the 2 interpretations. So one interpretation is to say, and you don't need to write this down, that for every kilogram you put on the surface of the planet, it will experience a force of 486 newtons. But the other interpretation is to say any object moving under the influence of gravity on the planet will accelerate downwards at that rate of acceleration in meters per second squared. Which leads us to a couple of questions. What is the weight of a 12 kilogram object on this planet? Well, weight is mass times G. So it's 12 kilograms times 486 newtons per kilogram. I'm going to carry all of my decimals. 5,827 newtons. I'm not quite exact on this, but a 12 kilogram object, if you get a 5-gallon water jug, those blue plastic jugs, and you lift it, that's a little bit more than 12 kilograms, but let's call it 12 kilograms. The weight of that single jug on this planet would be 50 times greater. Yeah, they are almost 20. They're actually about 45 pounds, which is just about 20 kilograms. So one of those water jugs kind of half filled up. But you get the idea, it's quite heavy. Second question, if the 12 kilogram object was thrown into the air, well, okay, let's forget about how you're going to throw this into the air. Right? Could you imagine even throwing one of those water jugs, which is just about 20 kilograms in the air? That would be really hard, and you want to throw it at 20 meters per second. So somehow we've got the technology to propel this thing upwards at 20 meters per second. We want to know how long it's in the air. Well, I'm going to do the time to the top and then double it. So we're only worried about the time to the top, and then we'll have to add the time to the bottom, which is the same. I can do VF equals 0 now because it stops at the top, and I can use A equals 486 meters per second squared, and it's negative. It's a kinematics question. That's all that's going on here. We can use A equals VF minus VI over T. This is definitely a case where you don't have to use negatives if you don't want to, but I think we probably should. Negative 486 equals 0 minus 20 divided by T. So T is equal to 20 over 486. carry all of your decimals for your g, you get 0.041 seconds. So I think you have to try to wrap your head around this. Somehow you have the muscle power to propel this object upwards, and when it leaves your hands, it will leave at 20 meters per second, and then it will be back in your hands moving downwards at 20 meters per second in less than 5/100ths of a second. And there are planets like that, not in our solar system. So there is an assignment attached here. There are a number of questions that I've typed out. I think if you do the questions I've typed out, that's good enough. I don't think you need to do the textbook questions. I've included them as number 9, but you don't need to. And that's what you're working on today.